Hello there, this is the last video on electrostatics. So I'll be covering three topics. They're not very different, very similar topics. So displacement, what is this? Susceptibility and energy in dielectric medium. Yes. So first is electric displacement. It is represented by a d bar. But before writing down what is d bar, we'll just write down Gauss's law, which is this one. Divergence of electric field is nothing but rho by epsilon naught. My rho can be written as the volume charge density of free charges and the volume charge density for bound charges. After doing some here and there, you'll get this one. So this quantity epsilon naught E bar plus P bar are polarization. This is polarization. This quantity is nothing but electric displacement. So I can rewrite Gauss's law in this way. Divergence of d bar is rho f. Rho f is volume charge density of free charges. If I integrate this one, I'll get, if I integrate volume charge density across its volume, I'll get the charge back. Very much obvious. Uh, and I know my rho f is divergence of d bar. Using Gauss divergence theorem, I can write this one now. Surface integral of d will give me qf. Gauss's law, we have two forms, differential form, integral form, using electric displacement. Nice. The left side is differential form, the right side is integral form. Okay, that is electric displacement. There's some question there. They were asking why is sigma b not accounted for in Gauss's law, or why are we not using sigma b in Gauss's law for dielectrics? The reason was this one. Uh, if you think why is the question valid, uh, wherever you see there is only rho f, there is no sigma f or sigma b or whatever. There is no sigma b anywhere in these equations. Okay, so this is the reason. If you try to take the volume charge density on the surface is very thin, so its volume is zero. That is, yes, the surface is like 2D, the volume is zero. If volume is zero, my charge density will try to go to infinity. Numerator is some finite value, some charge is there, some surface charge is there, but volume is zero, so this will tend to infinity. And if rho b tends to infinity, I know my rho is divergence of E, and rho is nothing but rho f plus rho b. If rho b is going to infinity, this will go to infinity. Divergence of E will go to infinity, and that is a problem. Because it is a problem, we are not directly taking sigma b into consideration. It's about some discontinuities. Some problem is happening here. I mean, this is a very sufficient reason to say why we are not considering it. You could investigate this on your own by yourself later. This is none of my concern. Moving on, now we'll try looking at similarities. Try to look at similarities between E bar and D bar. Are they completely similar or are they different? The green box mentions their similarities and the red box mentions their differences. Divergence of E bar is rho by epsilon naught. Divergence of D bar is rho f. Very similar. Is it rho f? Is it qf? No, anyways, it is. It's rho f. It's fine. Surface integral of E bar will give us q by epsilon naught. This will give us qf. The difference is this one. The curl of electric field is zero, but the curl of electric displacement is not always zero. For this to become zero, you need your polarization to be zero, but polarization need not be zero always. The other difference is this one. I can write this electric field as uh, 1 by 4 pi epsilon naught q by r square, Coulomb's law, but then there is no such uh, D will not satisfy Coulomb's law, that is not valid. The other difference is this one. There is some potential in the sense there is some scalar field associated with this vector field. There is no potential for D bar. So I know E bar is negative of gradient of V, where V is a scalar field. I cannot represent D bar as some gradient of scalar field. Not possible. Not valid. So these are the differences and similarities between E and D bar. There is more. There is something called the boundary conditions. If you know, if you look at the boundary conditions for E electric field, which we've looked at before in one of our previous videos, E perpendicular above minus E perpendicular below will give us sigma by epsilon naught, and the difference of their parallel components is zero. But in this case, this is not zero. Derivation is none of our concern. This is the final result. Uh, so this is also how D is different from E. Both of them are not the same. So they can't be both interchangeably used. How nice. Is this the last topic? Probably. Oh, there's more. Anyways, so linear dielectric and electric susceptibility. I got it right. So there is this formula over here. Polarization is nothing but epsilon naught chi into E bar. Here, chi is the electric susceptibility. It depends on the material, and it is a tensor apparently. I just realized it. I, it Someone just told me it's a tensor. But you can treat it as a number for a while. Nothing's going to happen. So for a linear dielectric, we know that T bar is epsilon naught E bar plus P bar, and this formula is telling that P bar is epsilon naught chi E E bar. Just substitute it here. You'll get all of this. Take things common. Then we have this new variable epsilon r. Epsilon r is relative permittivity, or commonly known as dielectric constant. All of you know what dielectric constant is. It is given by this formula, the permittivity of the medium divided by permittivity of free space. I can also write it as 1 plus chi e, where chi e is the electric susceptibility. And the product of epsilon naught and er will give me permittivity of medium. Nice. Non-linear dielectrics, we are not concerned about it, but for your information, there will be higher powers of uh, susceptibility and electric field. So this is some interesting bunch of formulae. Nice, beautiful. Yes, last topic in electrostatics. How nice, very fast. We got through it very fast. Energy in dielectric, or whatever, dielectric medium, whatever, polarizable object, so on and so forth. Without dielectric, we found out in one of our videos that work done on energy stored is nothing but half epsilon naught, and then you do this integration E square theta whole space. If this were in some dielectric medium, the only thing that would change is this one. You would have to multiply the old result with epsilon r, dielectric constant, or relative permittivity, whatever you would choose to call it. And this product is nothing but epsilon, which is uh, what is it? Permittivity of the medium, right? And I know that permittivity of the medium into E will give me d bar. So that is how this came about. I can write E square as E bar dot E bar. So yes, this is the final solution, energy in dielectric. And this is the final topic of electrostatics. I'll try uploading magnetostatics videos later, maybe. I'll let you know. Uh, it's too late now. Have a good night. I mean, it's night for me. I'll go sleep. Thank you. Bye.